number of participants is starting to increase now.
Yeah.
This is also being live streamed through YouTube. So some of them will be going straight there. We won't see them at this stage.
That's true.
So we just wait a couple of minutes and get started. So I guess we can get started so that we don't miss our schedule. So welcome everybody, and good morning, good afternoon, good evening, according to your time zone. This is the 5th webinar of the Trevor Platt Science Foundation. As you know, this is an international organization dedicated to capacity building of science, research, education related to our environment, especially our oceans, with the aim to work towards stewardship of our planet for future generations. Today's webinar is one of these capacity building activities of the Foundation. And we have the pleasure to have today Dr. Jeremy Weardle from NASA. And before introducing his talk, let me tell you briefly about Jeremy. He's an oceanographer on the Ocean Ecology Laboratory at NASA Goddard Space Flight Center, where he also serves as project scientist for PACE. Jeremy resolved to become a marine scientist in 1988 upon his return from an 8th grade science trip to the Bermuda Biological Station. And he joined the Goddard Space Center in 1999, where he has remained ever since in the pursuit of improving our understanding of the ocean's biological responses towards changing climate, mainly how the spatial distributions of phytoplankton communities evolve over time. Given that Jeremy wears a NASA badge, his mandatory secondary interests extend to the more challenging aspects of satellite remote sensing, including the on-orbit calibration of ocean color instruments, the development of remote sensing algorithms, and the validation of satellite-derived data products. This, in combination with his subject, matter living in a three-dimensional fluid on a rotating ellipsoid, create a research environment packed with opportunities to contribute to NASA's pursuit of a better understanding of our home planet. And with that, I leave Jeremy to offer us his talk, which is entitled Keeping Pace with the NASA Plankton Aerosol Cloud Ocean Ecosystem Pace Mission. Jeremy, the floor is yours.
Thank you, Vivian. So the mic working okay? Okay. Thank you all very much for the opportunity to chat. We're a recently launched NASA mission for which I serve as project scientist. So really enjoy this part of the job, which is, communicating how cool we all think that this mission is. So I'm very appreciated for the chance to see you all this morning, afternoon, and evening. So thanks so much. Vivian, I'm really sorry to make you say all of that in my bio. I clearly need to make it a little bit shorter. So no need to really elaborate much on who I am or what you're getting, other than to say I'm an oceanographer helping run a mission that is multidisciplinary. So bear with me as I muddle through the aerosol and land components of this story. But kept this figure in anyway because it's a really remarkable image of the observatory that we'll be talking about today, and gives you some context for its size. I'm about 2 meters away from it, so it's about as tall as I am. And I didn't get to go into the clean room all that often, but I can tell you, having watched this mission for 20 years, to be able to stand next to it is one of the most profound moments of this experience. All right, so just starting really at the top here, what is PACE, and what are the earth science missions that operate like PACE? Well, what I think is really amazing about this is we're in orbit 700 kilometers above the Earth's surface, and we make the invisible visible. And it's really cool. No matter what audience that I'm talking in front of, whether it's at a bar, something like this, or even, in front of management, just the ability to say we can see invisible things from space is a lot of fun. And in this case, we're really just talking about phytoplankton, and we're talking about atmospheric aerosols and a few things in between, which we'll dive into a little bit more as I go on. So really the talk kind of manifests in 3 different parts. I'm sure as amazing scientists or practitioners of environmental science, you know a lot of this, but we'll kind of for fun step through why we use satellites to reveal this invisible series of universes, but also talk about why NASA and all of our international partners who are doing equally great work are trying to study phytoplankton from space, and then where PACE fits into all of this. So studying the ocean is hard to begin with, and it's very big. This isn't easy water along the coast, even though it's accessible if you spend any time trying to collect samples in. So how about going on ships? So really what I'm just showing you here is that while I've wanted to be an oceanographer my entire life, I do realize that sampling water is very difficult. It's just not an easy task. And that's the end. Why don't we use robots everywhere? Which I know isn't necessarily, true for everything, but I just love that video. And it shows some of the other challenges of, autonomous vehicles and things like that, and what they face in terms of ocean sampling as well. But the reality is, we have 71% of our home planet covered in water. It is a rotating fluid. It's in 3 dimensions. The Earth is spinning. It is incredibly difficult. It is impossible to be everywhere all the time. And so without the vantage point of space, there are so many connections and processes and things that are happening that we just can't miss with aircraft or autonomous vehicles or shipborne sampling. It's just not possible. So I would never suggest that a remote sensing measurement from orbit can replace field sampling, but really you need it as a complement. Otherwise, there's just too much going on too many spatial and temporal scales that you can't see unless you have eyes in the sky. And so getting to the why phytoplankton, well, they operate effectively just like land plants. They photosynthesize, so they're taking carbon dioxide and turning into sugar and cellular material. So this transformation is incredibly important to all life on Earth. They also produce oxygen. And phytoplankton, just like land plants, come in many different shapes and sizes, thousands. They have different nutritional values. They sink at different rates. They feed different kinds of fisheries. As you can see on the right-hand side of this figure, they play a major role in how carbon and nutrients are recycled in the upper ocean and then exported to the deep. So this is all really to say, when you're looking at the acronym of PACE, the P is on the left and the E, the ocean ecosystem, is on the right. And we really need to understand distributions of these players. I mean, I often would go in front of my management talking to PACE and ask them a really simple quiz. Do you like eating? Do you like breathing? If you've answered yes to either one of those, well, you like phytoplankton, even if you're not in view of them and you need them in your life. So how do we do this from space? Well, we have the benefit that while they're very, very small, they tend to form in major spatial geographic blooms here. So in this case, you're looking at a coccolithophore west of the Celtic Sea. While it is 10% of a micron, you're looking at volumes that are on orders of thousands of cells per milliliter. And so your eye is just showing you, hey, there's something in the water in this image. And we know it's phytoplankton because of its color. And so we'll drill onto that later. But if that doesn't make intuitive sense, think about a hair on my head here. If I pull one out and hold it in front of the camera, you can't see it. Just like a single phytoplankton, you're often not going to be able to see them with your naked eye. But if there is enough in a colony or on my head, then you can see that something is there, that there are hair here. And taking this analogy a little further, and jumping ahead a little bit, you can see changes in abundance over time. When I started PACE, I had a full head of hair. 10 years later, I clearly do not. And so there's a time series of the abundance changing, and you can do the same thing when you're looking at these phytoplankton blooms. And then, of course, there's the color aspect of this. I'm giving you a little teaser here on how this all works, but these instruments that observe phytoplankton do so by just looking at colors of a rainbow. And same thing, in terms of a time series sense, when I started working for PACE, I had nice, luscious brown hair, and now you can see it is almost gray. So the satellites are operating just like your eyes looking at my absent head of hair here. So there's going to be one terminology change as we go through this. And I've been using the word phytoplankton all along here, but the core historical measurement of phytoplankton from space is in the terminology of chlorophyll A, which is a photosynthetic pigment that is ubiquitous in all photosynthesizing organisms. And so right now, as of, pre-PACE and a few other instruments launch, we were observing chlorophyll to get to phytoplankton abundance. But since chlorophyll is ubiquitous, it doesn't necessarily tell you directly what phytoplankton community is there. So we're going to come back to that in a bit. Now, I've sold up phytoplankton as being the best thing in the world, and in many ways they are. I think there are plenty of people on this call who would agree, but realize also that they can be harmful. In fact, there are phytoplankton out there that are actively trying to kill you. So this image on the left is Lake Erie, which is one of the Great Lakes in North America. And all of the green that you see on the western side of that image is a harmful cyanobacteria, so blue-green algae, that contains microcystins, which is a neurotoxin. It is a nasty little thing, and you don't want to be swimming in this kind of water. You don't want your pets in this water, so forth. Middle image here is the water intake for a city on one of the Great Lakes, so that you can see There are a lot of benefits to study phytoplankton, also for societal benefit, to know when the nasty ones are there. And there's a ton of recreational and socioeconomic value in being able to monitor these phytoplankton from space as well. Okay, so let's elevate ourselves above the sea surface into the atmosphere. Basically, we are trying to solve the same kind of problem. Today, with MODIS and VIIRS and ULTRAVIOLET and many other instruments, we are very capable of determining the presence of absorbing aerosols, in terms of their abundance. And an aerosol, oh, sorry, I said absorbing aerosols. I mean atmospheric aerosols, any aerosol. And the terminology here is really simple. An aerosol is anything in the atmosphere that isn't a gas. So clouds are actually a form of aerosol, but we're going to, talk about them differently in the context of this presentation. What I'm really talking about is everything that ranges from pollen to sea salt to desert dust to haze to smoke to volcanic eruptions. And they all play a lot of different roles here. And where PACE and other instruments come in is the speciation of these atmospheric aerosols. We can tell today that they're there, but we don't necessarily know which aerosol is there. And you can see from the scanning electron microscopy on the bottom of this that they too come in all shapes and sizes and thus play different roles. So there's a climate aspect here and there's an air quality aspect here. And it's kind of captured in this one little cartoon. As you have solar irradiance hitting Earth, that irradiance can either be absorbed by Earth or reflected back out into space. And of course, there's also emitted thermal energy here. That's where the greenhouse gases really come in. When you're talking about aerosols and clouds, this reflection and absorption dictates how much energy is absorbed by the atmosphere. And that in turn, of course, impacts our climate here. And there are some aerosols that warm our atmosphere by absorbing energy, but then there are others that cool our atmosphere by reflecting energy. So knowing this speciation is incredibly important in terms of better understanding how our home planet is evolving with its changing climate. Okay, so how does this all work? I alluded to this a few different times before, and I'm going to give you an oceanographic perspective because I'm an oceanographer, but the same is true for atmospheric science in many ways, terrestrial science as well too. So the color of anything we look at is really determined by the interactions of incident light with whatever it's beating down on. So in this case, you have happy little photons of all different colors coming from the sun. They make their way through the atmosphere after being absorbed and scattered and perhaps interact with the ocean's surface. In this case, if they are fortunate enough to penetrate the ocean's surface, they suffer one of two fates. And this is true of any time a photon interacts with anything. It could be a soda, it could be blood, whatever, oil, two fates. It's either going to be absorbed and that energy is going to be transformed into something else like heat, or it's going to get scattered or redirected into a different plane. And how absorption and scattering happens is dictated by what's actually in this case, the water. So you have phytoplankton, you have seawater, you have everything else dictating how light is being scattered and absorbed. And you can see that the nature of the color, and what I mean by that are, shown here in the lengths of these arrows, changes. So you have white light from the sun, but then it's starting to interact. And in this case, you can see that all of the red light is going away. And that's true of any body of water. You don't see it in a glass, but you can start to see it in a pool. Then if you get to a lake, all the red light is gone, which is a really cool camouflage mechanism for certain fish. But in this case, you have blue light and green light penetrating deepest. That's telling us something. This scattered light maybe exits the ocean, which is what gives it its color, which is what we can see with our eyes. If those photons of different colors find their way all the way back to the top of the atmosphere where the satellite can see it, these instruments operate a lot like your eyes and are just photon counters. But unlike your eyes, they are counting one different color at a time. So in this case, really, just so you know, these are passive instruments, meaning they're just observing how sunlight interacts with the medium. And so their core data products are accurate measurements simply of light intensity of different colors of the rainbow from the ultraviolet into shortwave infrared. And those are the core measurements that we use for all of the disciplines of PACE and all of the other instruments, the ULTRAVIOLETs, the VIIRS, and so forth. So looking at this one more time in a different way here, this is a true color image of the northern Gulf of Mexico from the Mississippi River Delta going south. And these different boxes, show different colors of water. And then on the right-hand side here, what you're looking at are spectra that are representative of those different colors. So colors of the rainbow on the x-axis, a proxy measurement of what the satellite sees on the y. And what I want you to see here is that when you're looking at really brown water, the blue and the red light are going away, and you have all of those greens and yellows that are forming that little hump in the top spectra. As you start going down, you can see the shape of this is changing. At the very, very bottom, when it's blue, the red light is going away, only blue is left. And so that's the color that we're seeing. So really, we're just looking at accurate measurements, one wavelength at a time, of these different colors. And from that, we can relate color to a geophysical property that we actually care about. So talking about chlorophyll again here, this is an example of a 40-year-old heritage product from an ocean color instrument. And all it is really a ratio of a blue wavelength of light to a green wavelength of light on the x-axis, and then chlorophyll on the y-axis. And these are for measurements in the field. Note they're both in log scale, but you can see there's a fairly well-behaved relationship here. So what I'm saying is that if I can be given a ratio of blue to green light, I can give you a very credible estimate of chlorophyll A. If I have an estimate of chlorophyll A, I can start making inferences about the abundance of phytoplankton in the water. And then when you're doing this from space, you can start creating these maps. And so in this case, you're looking at Chesapeake Bay, which is the nearest body of water to me. And you filled in all the gaps. This is one day, one image, and you got the whole view of this estuary. The reds are high abundances, the greens are middle abundances, and the blue and the purples are very, very low abundances. Now, if you make these measurements long enough, you can start doing fascinating things like this. So what you're looking at is 25 years of ocean color observations from 3 different satellites compressed into 2.5 minutes. To me, this is an equivalent contribution from our community as like the moon landing. Just our community, the Royal Global community, this contribution of watching the heartbeat of our planet is incredibly profound. So again, getting to the color bars, the land is pretty intuitive. The browns are deserts, the greens are forests, the whites are ice. In the ocean, the deserts are represented by the purples and the dark, dark blues. The forests are represented by the reds and the greens and the really warm colors here. And if you know what you're looking at, and I've stared at this a lot, you can start seeing patterns change over time. The ocean deserts are starting to get bigger. The reds are becoming more intense. They're starting to appear at places where they didn't before, or they're changing the timing on seasonal cycles of when they appear here. So you have a lot of information that is really talking to how is the ocean responding to changes in our home planet over decadal time series here. But again, I'm not able to really tell definitively what phytoplankton community is here. I'm just telling you that there's a lot versus a little from imagery like this. But as a personal aside, I think this ought to be playing in everybody's office 24/7. And anytime you get stressed out, you just look up and watch your planet breathe, and it's really, really cool. So where do we want to go from here? Both from a phytoplankton perspective and an aerosol species perspective. The upper left-hand corner is a representation of 4 different phytoplankton communities and their evolution over time. The bottom right-hand corner is the same, but for 5 or 6 different atmospheric aerosols. These are beautiful, but they are modeled data. We don't have direct observations that are adequate enough to do what these models are doing. And that's where we're going with this next generation of satellites like PACE. We want to be able to do this with direct observations from space so that we can complement models, but also not worry about fidelity of models or use the information to feed into models to improve them so that we have all of this new additional information to do these 2 things, but from the vantage point of remote sensing on satellites. Okay, so let's talk about the advances of this kind of instrumentation, where we are today and where we're going forward. And this starts to get into the why PACE and why hyperspectral and why the evolution of all of these instrument systems from international agencies. Well, if you're looking at the left, you can see 4 heritage NASA missions ranging from the late 1970s CCCS, which is proof of concept, all the way to VIIRS, which is flying today. Color bar just represents all of the visible to shortwave infrared color that we're interested in. You can see that these instruments are what we call multispectral, meaning they're measuring multiple different colors, but not a continuum of color. Now, to their credit and their contemporaries, the colors they're looking at are really intelligently placed to tease, for example, a phytoplankton or chlorophyll signature out of the background of all of the color. And we've been able to do really transformative work over 4 decades with instruments like this that are only measuring, say, 2 blues or 2 greens and a couple of reds. But the reality is even though we refer to our home planet as the blue marble, the ocean isn't just blue. So 2 blues aren't enough. It's really got a ton of green in it, but it doesn't have 2 greens. It's got 150 shades or something like that of green. And you can see this when you walk through the forest. There are so many different greens when spring has sprung. And that variation in green tells your brain, hey, that might be a different plant, or the health of that plant is different than what I might expect or what I saw 2 weeks ago. So getting to all of these different subtleties and changes in the shade and the hue of different colors is incredibly important. And so this move to spectroscopy or hyperspectral measurements, where you're measuring a continuum of color with few gaps, is really important. And so here's just one quick example of this. I was fortunate enough to have great committee members and mentors when I was working on my PhD. And we did a study 10 years more ago in the Northern Arabian Sea. And it's in a really, really fascinating place for a lot of different reasons. And one of them is that it is undergoing a really remarkable community structure shift during various monsoon seasons, especially the winter monsoon. And so the normal ecosystem is typically dominated or was dominated by diatoms. Form the base of the food chain, higher tropho levels, zooplankton, fish, birds, all of that. And what has been observed in the field is a big bully has kind of come in, known as Noctiluca. It's a heterotrophic dinoflagellate, and it's completely changing the dynamics of this incredibly complicated ecosystem. But as you now know, studying huge bodies of water is hard. And so you really benefit from having synoptic imagery from space. We don't have time machines yet either, except for satellites. So wishing you had been out in the field collecting data 10 years ago, you can wish all you want. That's not going to happen. But these long-term satellite data records really are time machines. They're preserved. And as you get smarter or you come up with new ideas, you can go back, reprocess them, or apply a new algorithm and learn something new about what's been going on in the past. So in this case, satellites are really valuable to study this part of the world. But when you have a VIIRS type instrument that is only measuring, say, 5 visible colors, you don't have a lot of information. And so what you're looking at the plots on the right here are color on the bottom, wavelength from ultraviolet into near infrared from left to right, and then a normalized absorption, which is a proxy for what the satellite's seeing. And you've got the diatoms shown in black and the Noctiluca shown in red. And if you look right around 550, you see that that's really the only unique piece of information to tell these two communities apart. And it's not enough. So this expansion into spectroscopy or measuring the continuous color, you see PACE OCI down there as an example, and there are enough differences in the spectrum, you now have some information to tell these two communities apart, which is really, really remarkable. So this is one of the major advances of PACE. And I want to be completely acknowledging that there are predecessors to PACE that are doing wonderful hyperspectral measurements from orbit. Where PACE comes in is it's the first time ever we've had these measurements on daily scales. We can see the entire globe every 1 or 2 days, and that has not yet been done before. So it fills a really interesting niche. Now, I haven't talked about some of our other instrumentation yet, but here's a nod to them, where we're going to really start advancing how we view our atmosphere, atmospheric aerosols and clouds, is through multi-angle polarimetry. So typically, in most of our ocean color field, we're used to instruments that really only have one viewing angle. And what that means is when you see a piece of real estate on Earth, you're only seeing it from one angle. When you do it through multiple angles, as you can see on the left two panels here, the way what you're looking at manifests is different. And so there's a lot of information here just by changing your geometry. So this multi-angle ecosystem is really, really interesting. And then when you start thinking about polarization of light, as we all know, light travels in horizontal and vertical directions, is electromagnetic field, and there's some circular here. What we see with our eyes is total intensity. What you see with a lot of our heritage instruments is total intensity. But if you can separate the polarized signal out of that, it is an entirely new way of viewing what you're looking at. So think about, in the simplest sense of putting on polarized sunglasses, you're looking at a reflective surface like the water, and you tilt your head, you can see that how the water looks starts to change. Well, we can do this with instrumentation and spectrometers and radiometers too. So the combination of this multi-angle viewing and being able to measure polarization state is really a quantum leap forward in information content. And from an oceanographic perspective, this is really interesting. From an atmospheric perspective, this is where that community is moving forward to next, at least in passive remote sensing. So in terms of pace, I've talked a lot about this. What are we talking about in terms of products that we hope will become available to you? These are our expectations here. We'll just cycle through that really quickly. So again, we're really talking about passive instruments here. There's no laser coming down. They're like in the LiDAR, there's no radar. They are photon counters. And so when they're staring down at the top of the atmosphere, what they're seeing is the result of these photons interacting with everything in the way. So, it's the atmosphere, it is reflection off of sun glints and land, and it's whatever's going on in the ocean. And this is why we're able to have atmospheric, terrestrial, and oceanic communities here. Now, from an oceanographic perspective, the atmosphere is a real nuisance. It's like 85 to 95% of the signal. So it is total noise and a huge number that we need to get out of the way. Atmospheric community, the ocean's a nice boundary condition, but it's a nuisance for them as well. But we're starting to work well together, which is why we have these series of products that complement each other. So starting at the very top, talked a lot about aerosols. The products that we believe we're going to get from polarimetry and to a lesser degree from OCI are listed here. It's basically all of the microphysical properties of these small multi-shaped particles, their absorption, size distributions, carbon content, and then really importantly, the thicknesses of their layers and where they are in the vertical column of the atmosphere. The same is true clouds, their microphysical properties, their optical depth, meaning their thicknesses, basically the way they attenuate light, their height, their thicknesses, so where they form physically. Also, really interesting, we can get to thermodynamic phase function here, whether we're looking at a liquid cloud or an ice cloud. So putting this all together, you get a lot of new information about our atmosphere and where we, as a mission, truly fit in to furthering climate research is by measuring all of this together, we can start to understand the interactions between the two. And if you look at various IPCC reports where they're assigning error bars to the various contributors to warming and cooling of the atmosphere, it's these interactions that are least well understood with the largest error bars. So our mission is to start compressing them through these measurements. We are looking at the ocean surface, so it's albedo. They can do some really interesting things with regards to whitecap fraction and angular light distributions. And then we do have some projects out in the community that are proposing to use polarimetry for oil slick detection too, which I find to be very interesting because it's a much smaller spatial footprint that we can use than what you're getting from synthetic aperture radar. It's crossing the air-sea boundary here, very similar properties here, and in the broadest sense, we're looking at light penetration and the light that's available for photosynthesis, light transmission, all of the optical properties related to absorption and scattering. With polarimetry, we think that we can get to indices of refraction of hydrosols, which is brand new and very, very interesting. As you now know, one of the promises of PACE is to get to anything related to phytoplankton in this community structure and physiological health. So we'll be doing retrievals of photosynthetic pigments, fluorescence, and different community matrices. We're not limited just to the organic universe or the algal universe. It'll be particulate carbon, particulate inorganic carbon, suspended matter. And then when the water is shallow enough such that light penetrates all the way to the bottom and then back through, there's information that can be used for bathymetry classifications as well too. And again, I've mentioned terrestrial land applications a lot. It does not fit into our acronym. We should have been PLACE instead of PACE. We are not, but there's a lot of great energy in using this hyperspectral signature for some novel terrestrial retrievals. And even though, as you'll see, our footprint is pretty big relative to, say, Landsat or MSI, PACE provides a really nice pathfinder in terms of using full spectroscopy to get to vegetation indices and other matrices.
5, 4, 3, 2, 1, ignition, engines full power, and liftoff of Falcon 9 carrying NASA PACE. Go Falcon, go NASA LSP.
So I put this in for two reasons. One, it's a really nice transition from 20 years of research into, hey, we're finally on orbit. And two, because I can't stop watching it because it was so much blood, sweat, and tears for hundreds of people,
MVAC engine show
members,
started.
and to see this realized is,
Stage separation.
it chokes me up every single time.
MVAC ignition.
And then there's a moment coming up here that reminded me of dropping my daughter off at kindergarten, 15 years ago, watching my son go to college for the first time. Everybody's leaving the nest, and you just gotta be a good parent, and this is it. The last time, laid eyes on her.
Payload separation confirmed.
And she's doing really well so far. So we launched early morning, February 8th. Today is the 175th day of PACE. So we're having this conversation pretty early into the mission, but everything is going well. We'll talk a little bit about that before I take your questions. I'll let you know where we are. Okay, so talking a little bit more about the observatory, because we really haven't done that yet. You have a beautiful glamour shot here from a CAD model that shows you kind of how everything fits together. We'll show you the different instruments sequentially here, and you know why PACE exists now. I spent the last half hour talking about it, but you can read it again. Legacies here, at least from a mostly NASA perspective, are CZCS through VIIRS for ocean color, but again, MARIS, ULCI, GLI, SGLI, OCTS, so many others, certainly contributed. And then from the multi-angle and polarimetry, MISR and Polder. Key characteristics of our mission. I mentioned very quickly that we're 20 some years old. In the United States, this mission is old enough to have an alcoholic beverage. A lot of energy went into people thinking about what this should be right around in the very early MODIS and VIIRS era. Fast forward to 2014, we got our direction to build. The engineering design life is 3 years, but we have somewhere between 10 and 20 years of propellant, most of which is reserved for re-entry. So long as everything continues to perform, we're hoping to have a multi-decadal life. Like most Earth science missions that are passive, we're roughly 700 kilometers. We're polar, ascending, so we go on the daylit side of the Earth from the South Pole to the North Pole at a 98-degree inclination. So it's roughly a 90-minute orbit, 14 and a half orbits a day. So we really cover the entire globe with our wide swath instruments, and it's got a 1 o'clock equatorial crossing time. So, wherever you are in the world at 1 p.m., you can look up, give it a little wave, and chances are it's looking back down at you. So I'll walk through these a little bit slowly here, but with you, it's a 3-instrument payload. I won't belabor this because you'll see the specs a few different times. But where OCI comes in, which is the primary instrument for our mission, is spectroscopy, truly from 320 nanometers continuous all the way to 890. It's listed as 340 here because that's our requirement, but the spectrograph can go down to 320. The data aren't perfect there, but we can shine light on those detectors. The spectral step is 2.5 nanometers, and it's got 5 nanometer spectral resolution at every step. And then there are 7 shortwave infrared bands. I already mentioned the global coverage. It's a 1 kilometer footprint at nadir. The instrument tilts, so it's really closer to 1.2. And then there's a 4.5 tilt as well too, which we can talk about later a little bit. The meaning that basically, like CWIFS and CZCS, OCI is an instrument that looks away from the sun. And that's really important to increase geographic coverage in areas where there would be sun glint. We have 2 contributed multi-angle polarimeters. The first is from the University of Maryland, Baltimore County. So I live in Maryland, just north of Washington, D.C., and this is where NASA Goddard is located. And about another 10 kilometers farther north is this university. And they have a wonderful little instrument. It has 4 visible to near infrared bands. It's super wide swath, 2.5 kilometer footprint. It's hyperangular, meaning that it is measuring a continuum of angles 60 in its red band. And because of that hyperangular capability, the cloud capabilities and the retrievals it can produce far exceed what you can do with OCI alone. Then the second is SPEX-1, which is a contribution from a consortium of organizations in the Netherlands. It is also a multi-angle polarimeter, but it is hyperspectral. So there's a continuum of measurements from the ultraviolet into the near infrared, which is really great for advanced aerosol retrievals. And its capabilities with its 5 viewing angles exceed what you can do with OCI alone. And its footprint is 3 kilometers at nadir. So I'm basically going to say that information 3 times, just to slowly let it drink in, because I know a lot of this is kind of akin to drinking from a fire hose. So here is a visualization that might put some more of this into perspective and help indicate how these instruments play off of each other. So this is our ascending orbit at 1 p.m. I mentioned all of these key characteristics before. Now we're going to zoom into our 3 instrument payload. So OCI, again, is a hyperspectral scanning radiometer. What you can see here is the width of its swath, which is what allows it to do 1-day global coverage. We cut it to 2 days for some geometry considerations for ocean color, but for atmosphere studies, it's 1-day coverage. And you can see that there is a 40-degree tilt, 20 degrees aft as it ascends over the South Pole, and then 20 degrees fore. This is HARP 2. In this case, you can see what I mean by multi-angle viewing, and you can also see that it is a very, very wide swath here too. 60 angles in the red, and then 10 viewing angles for the blue, green, and near infrared. Now we have SPEX-1. For comparison, it is a much narrower swath. It's got roughly a 30-day monthly repeat cycle here, 5 viewing angles. But the text in the upper right gives you a sense of the number of steps for both polarization and for total intensity. Pause for a drink, let this start, and you will see the comparison of these swaths. So we got a pass of SPEX-1. While you're watching this, I'll just share that data latency, our requirement is 24 hours. But the data are usually available from collection to level 2 online or in the cloud within 6 to 12 hours here. And this is all publicly available data and as near real time as we're able to do. So kind of tying a bow on this, you can see that the synergy across instruments is really, really powerful. You've got all of the advances of OCI and the 2 multipolarimeters, which are remarkable in their own right. But when you start putting this together, the information content exceeds anything that I believe NASA has flown or has planned elsewhere. And then when you start thinking about using this information with other satellite assets, it is really, really remarkable where we might go in terms of discovery as a community with all of this. So one more picture of the observatory. You saw this before with me standing next to it. Some information about the instruments. In case I'm going too fast, you can look at one more time. Well, I just say, hey, there are niches here that are not currently addressed at home or abroad, and this is where PACE fits in to the royal we here. This move from multispectral to hyperspectral radiometry, it's essential for moving forward in observation of aquatic ecosystems. There isn't anything planned so far as I know, although there's a lot of conversation across the pond here and where to go with this. But as of today, 1-2 day global spectral coverage, so a nice niche filled there. This ultraviolet information and the two 2-micron bands together are really fabulous for taking the MODIS and VIIRS heritage retrievals for aerosols and moving them forward. A lot of new information there. We don't have any thermal bands, so I don't want to oversell in any way what we can do with regards to cloud remote sensing. We can do it pretty well, but without thermal, you're losing a lot of information. What is really interesting for us, though, is that we're the only one with two 2-micron bands, one that is positioned where MODIS has their 2-micron band and one that is positioned where VIIRS has their 2-micron band. And those positions actually represent different thermodynamic phases for clouds. So if you're starting to think about continuity from MODIS to VIIRS, there are differences in those retrieval algorithms, and by having both, OCI can help bridge that gap in understanding. And as I mentioned, bringing in multi-animal polarimetry adds a ton of new information, also provides a pathfinder for what can be done with the soon-to-be amazing 3MI ecosystem and MEDUP and other polarimetric instruments, AOS and so forth. And then last, we didn't talk about it a lot. I'm happy to answer questions, but the fact that we have ocean color tilting again really does increase knowledge base of a lot of latitudinal bands that we haven't had since the demise of CWIFs. Talking about data quality here, while we're very early into the mission, it seems like, hey, you're 6 months in, but our field team, everybody who's been funded just really got started. So we have some indices of how the radiometry is performing from OCI. We're really excited about it. If you look at a blue band here, remote sensing reflectance at 445 nanometers, looking at VIIRS, looking at OCI, yes, there are coverage differences, but the retrievals are very, very similar. Oops, wrong way. And if you take certain points here, you can see VIIRS in the circles and OCI in the continuous line there. And what's really remarkable for me, or really relieving for me, is that out of the box, with just one new or on-orbit calibration, MODIS and VIIRS are retrieving roughly the same answer. So we like to joke with our NOAA colleagues who run VIIRS now that we finally have a tool with which to properly validate VIIRS. But this is very exciting for us. In terms of some, talking towards where we're going with this, some preliminary advanced products, US East Coast, so Western Northern Atlantic here. You can see a chlorophyll image from March. Well, we tried one of our community composition algorithms out on this. Here are some preliminary results from the Moana algorithm. And we're feeling pretty good about the fact that we can take this chlorophyll image and now separate into 3 different phytoplankton communities, the small guys, Prochlorococcus and Synechococcus, as well as the Pico-eukaryotes, the bigger guys that feed fisheries and so forth. So again, these are not fully validated, but we're excited about the promise of these retrievals, because this is the promise of what we're trying to do with this mission. Courtesy of the University of Maryland, Baltimore County, there are some advanced aerosol products from the Ocean Color instrument here, in particular ability to get a retrieval of single scattering albedo in the lower left-hand corner and aerosol layer height. This team has made a lot of progress since these first light images, but we were really, really excited to see them because these are retrievals you can't do with our heritage instruments. And then, of course, our polarimeters, both HARP2 and SPEX1 are really exciting looking forward. With all of these instruments, we're still learning how to fly them and drive the bus, but the preliminary results are really cool. And so just getting away from, typical aerosol contributions here, we're looking at sulfates and nitrates from SPEX1 on the upper left and black carbon on the right. These are courtesy of our partners in the Netherlands. And the fact that you can do some of these things now is really, really encouraging for the future. And we're just going to keep getting better, and we welcome the community too. And I want to, again, keep acknowledging our land community. So this is a normalized difference water index time series here that one of our local colleagues also put together for us. And it's new information for this community from space anyway. So it's exciting to see everybody moving forward. All right, I'm running a little short on time. This pretty much just tells you the same thing. If you go to the Science Visualization Studio, and I will put a link into the chat when I'm done, all of our PACE visualizations and animations are there. If I've piqued your interest at all, it's a good place to go. Where we are today. Okay, so we released data publicly on April 11th, 2024. That was 63 days after launch. So it's pretty darn early, but we were really pleased with the performance. This included level 1 radiometry from all 3 instruments and heritage ocean color products from OCI. All listed as provisional, meaning you can go to NASA Earth Data Search and get them today. Our first reprocessing was completed just less than a month ago. This involved the first use of our on-orbit calibrations for all 3 instruments. It also gave us an opportunity to release a second wave of test products from the Ocean Color instrument. This includes terrestrial and aquatic surface reflectances, about 10 different terrestrial vegetation indices, and our first crack at cloud optical properties and an altitude. If you go to the PACE website, there are release notes. It shows you how to get all of the data, walks you through it in hopefully a very friendly manner. But I want to show you the evolution that things are starting to move forward in terms of getting towards advanced products. Second reprocessing, which will be version 3, we're hoping will be conducted in our fall, so in the coming months, where we do our first system vicarious calibration for the Ocean Color aficionados. You know what I'm talking about. If not, ask me a question later, but it's another calibration step. And then another TBD wave of products. We're expecting to get our first OCI aerosol retrievals out there, perhaps community composition test products, and I'm really excited to start releasing some polarimetry derived products. So you know how this works. We don't have any predefined deadlines. We're basically learning as we go. All of our additional advanced products will be released pending collaboration with the algorithm originators. So the project, someone like myself working with the PI to verify faithful implementation and so forth. And these will generally start as global map test products that NASA Goddard releases through our archive, and then eventually get migration into NASA's Earth Data Search. We'll make them available via clouds and Worldview and so forth. Our website is dynamic, both in the sense that it resizes, but also that we have a fabulous web team that is continually making updates. It should, under the data tab, teach you how to get all of these data and what you should know about them. We're trying to be really honest with all of the warts there. So if it's not available today, it will be tomorrow or the next day. To accompany our complicated release notes, a nice visual tool that shows you all the places in the spectra that you might want to be aware of, because we're not doing everything perfect yet. So we have 2 spectrographs they cross. That's a region that maybe you want to avoid using, but we outline all of that for you. We have a technical report series that talks a lot about our design choices. And then honestly, if you're looking for simulated data characterizations, anything, this is your one-stop shopping for it. We have an active community. Hopefully many of you are involved or will get involved. That includes a science and application team, the pointy-headed algorithm scientists that, contribute algorithms for products or interpretation of the data. We have a validation science team, which is kind of the inverse of that. No hypotheses, no science, just go and collect data. They're out in the field now, so performance assessments should be rolling in the next month or 2. We have a really fabulous post-launch airborne experiment campaign being conducted off the US West Coast, California, in September. It involves 2 aircraft, a high-flying ER-2, a low-flying Twin Otter, and some at-sea work. So this is our really best shot at evaluating performance of those atmospheric retrievals that can only be done from the vantage point of an aircraft. And then we have 2 system vicarious calibration teams as well. So I'm bringing this up to let you know that these are happening. So hopefully you have some energy to check back and see how we're doing, but also to let you know that if your own research, all of these data will be made publicly available, not long after collection, within 90 to 180 days or so. They're available for you to use however you wish to use them. And if you want to stay more informed, we've got a great early adopters program in a community. If you go to the website, you will see a button right on the middle page that shows you how to join this mailing list. And that's the tool many of us are using to periodically communicate with all of you. Other assets that you might be of interest, we hosted a PACE class 2 years ago, summer of 2022. All of the lectures are available online. And next week, we're hosting a hackathon, a social coding event. And that's got 40 participants, with 10 coming from outside of the US. While it's too late for anybody on the call to join, all of the results, all of the code will be made available online at the conclusion of the class too. So there should be a lot of nice tools that help you interact with PACE data and, make that a nice clean process as well. So wrapping this up, really just looking at the middle bullet here, what I really want to say here is in the very, very biggest picture of all of this, when you think of NASA, you don't always think of Earth science. You probably rarely think about phytoplankton or oceanography. You're thinking of Hubble, James Webb, launches to the moon, and so forth. And, we've all really enjoyed a lot of these amazing imageries from Webb that has been this quantum leap forward from going from Hubble into the way we're going to understand our universe. For us at NASA, it's an equivalent leap moving from the MODIS ecosystem to the PACE one. It's as profound a step forward as this astrophysics and astronomy community has. And so any chance I get to say, hey, NASA and our partners outside of the US are doing amazing Earth science. These space agencies are incredible. And hopefully someday we'll start thinking about Earth science as the first thing we think of when we have these. So with that, I will wrap up. QR code on the side here. It should take you to the PACE website and everything else that I've told. I'm clearly losing my voice, so I will pause and thank you so much for your attention.
Thank you, Jeremy, for this talk about this very exciting mission. And so we open now the floor for questions. I see a few on the Q&A box. And please, Katarina, let me know if there are other questions from the YouTube channel. So starting by the ones on the box, well, I see that most of them you already answered them in your last slides of the talk, are related about the data itself. And it's from Norberto Scarlato from the Fisheries Institute at my hometown in Argentina.
Yeah.
And Norberto is asking whether the information gathered by this satellite is publicly available or restricted, and then how should it be cited? And well, that's the first question. I think you already answered it, but if you want to elaborate something.
Publicly available,
Yeah.
in most of the data access, there's a tutorial on the PACE website that shows where to access it and answers a lot of those questions as well.
Okay. And most specifically, he's asking about how is it shared with crop industries or ocean agencies? If there is any special link with industry or institutions.
So we've had, we actually have a nice link through an applications program that we developed starting in 2000. So, they were virtual for most of this, but we have an applications team embedded into our project, and their mandate was to seek out communities like that to bring in early adopters, those people who wanted to practice with simulated data, they were ready, but also to be traveling to underserved communities or different communities that might be aware of remote sensing, but, we're still mystified by it. So, those of us in the project, are starting to host more trainings, work with international partners for that. But we have this applications program that is actively trying to bring in these communities and make sure, ocean services, NGOs, international partners are all sufficiently aware of us and able to be trained or understand the accessibility of all of it. So.
Okay, thanks. And there is a question by Alejandro Clement. He says, I work in optically complex waters with hub fjords. Can we classify different species type with PACE?
That's the promise of it. There's been a ton of research over years how to do that. There's a number of success stories. what we're excited about is, given the increased spectral resolution, you have a lot of new information, you know, as I was saying, to get to different communities. So that's our promise. We don't have all of these products out on the street yet because we're still evaluating radiometry, but our goal is, you know, to do it with our science teams, to make these data as available to people like yourself so that you can start using it and tailoring regional algorithms as well too. So, I mean, that's, you're picking at exactly where we're going with this.
Okay, so a lot of work for the new generation to play with these hyperspectral puzzles.
I wish I were a student again. So,
Yes, and there is another question by Ravi Naik. Say, how best PACE works in polar coastal regions?
well, so the good news is that given its polar orbit, it sees that latitude a lot. The bad news is that it's cloudy and ice is a potential source of radiometric contamination. So those data are being collected. We never turn any of the instruments off. They don't collect data on the dark side, but as long as it's sunlit, it's there. And you know, there have been a number of studies using MODIS and VIIRS and other instruments about data collection and fidelity of algorithms, you know, in polar seas. But you know, as you're probably alluding to, I imagine there's still a lot of evaluation on the quality of these retrievals that needs to be done. But the data are there. So if it's, you know, in the case of ocean, if it's cloud free, you know, we've got a signal to work with.
Okay, thank you. So I don't have more questions in the box or in the chat. I will ask Shuba or Milton if you have any comments. Shuba, you're mute.
Sorry, folks. So, anyway, all I can say is that was a brilliant presentation, Jeremy. Fascinating.
Oh, thank you so much. I appreciate the kind words.
And it's a lot to look forward to. And like you, I too, it makes me wish I were younger and that we. But now we have to leave it to the youngsters to
Exactly.
fill in that promise, right?
Indeed. Indeed. Yeah, there would be I hope there's a lot of discovery. That's what energizes me at this point. You know, I'm going to go to this hackathon and not know how to do anything, but I'm excited to watch the discovery of the younger crew.
There will be at least one person from our lab coming to the hackathon next week.
Excellent.
I would also like to thank Jeremy for such an interesting presentation, and I will take the advantage of the shortcut here. Just a few short questions. Why not? Directly to the source. If the data is planned to be delivered at 10 nanometers resolution indeed, and as a surface reflectance or remote sensing reflectance?
So for remote sensing reflectances, it will be native resolution, which will be 2.5 nanometers for most of the spectra. Over chlorophyll fluorescence region and oxygen absorption region, it's actually 1.25. We have a finer step. It's only for the reflectance retrievals that we're doing the 10 nanometer step. So, and that some of that is, you know, the need of that community, but some of that is these data volumes are getting very, very big.
That's what I guess. So thank you for this.
You bet.
Vivian, there are some more questions now in the Q&A.
In the chat? Okay. Yes. Yes, from Shanta Achutanchaputi, sorry for the name. Is artificial intelligence introduced in this study?
Fabulous question. Yes. As you're probably guessing now, there is a ton of information and there's a huge volume. And so with our latency requirements and our ability, you know, our interest in being able to rapidly reprocess, you know, our heritage algorithms are very, very slow. They're used to dealing with, 10 wavelengths, and now they have 200, at least for OCI. So there has been a remarkable effort, within our group, our science team, and the community to start using machine learning and optimizations and so forth to speed all of this up. One good example would be our atmospheric correction process, the ability to use PCA and lookup tables to speed up the radiative transfer that goes on. So it's actually one other thing that I'm hoping comes out of this is, given the information content, and there's something like, if you take all three instruments, like 5,000 unique-ish pieces of information per pixel, that the data science community has their own little revolution in terms of how they use this kind of earth science data. And so I'm optimistic, that pairing up a scientist with a data scientist will really push both communities forward in terms of how machine learning and artificial intelligence is used. So yeah, we've already used it to answer your question.
Okay, yes. And there is another question from Norberto about if PACE is also oriented towards detection of microplastic pollution.
I get that one every time. I love this question, so I was going to leave disappointed if someone didn't ask. The honest question is, I'd love to be optimistic about this, but I'm not really sure. We've had previous science team members try to explore this through use of the shortwave infrared bands. I think there might be some value in using polarimetry for it, especially the combination of multi-angle and the polarization state. But it is really still a very outstanding research question. And I think the problem that most researchers are facing here is that while these plastics are abundant, they're not densely packed, and with photo bleaching and other things, they don't have a huge optical signal. And so there are still a lot of challenges to overcome. But again, I'm choosing to remain glass half full. We can chip away at this. I don't want to oversell it though.
Okay. So there is another question by Lasse Pettersson. It says, thanks for a nice presentation. Are there plans for continuation with the PACE 2 in order to become fully operational and have PACE EUV and ECVs?
You're picking at a scab here. There's a lot of conversations about that. There's no official plans in the book yet. There are some studies going on. If it were me, we would have started that activity, 5 years ago. So stay tuned. I'm being as hopeful as I can that there will be a follow-on.
Jeremy,
okay.
I thought NASA is also talking with the European Space Agency about continuity and.
Yes, yeah, which is the part of this that's giving me some hope for the future. I know, there's a few of us are on the advisory committees for like Sentinel-3 Next Gen. So I'd like to retire knowing there was continuity in hyperspectral from space, global hyperspectral from space. That's my next goal. Then younger generation, it's all yours. I'm going to go open a tiki bar somewhere.
Yes, I remember also the discussions at the last IOCCG meeting, the concern about following up missions. So there is a last question by Alejandro Clement, and I think it's more for Shuba. I see Shuba is here. With Trevor, they wrote several papers in relation of integration optical data from surface remote sensing signal. Any news about this?
Big question. I'm not sure I understand the question. I think if I'm reading this meaning.
Yeah, me neither. I think it's regarding also like following up generation.
Yeah, I thought that the question was about integrating satellite data with in situ data, perhaps about the vertical structure or something like that. Well, if that is what it is, then I guess that there is also another revolution happening on that front, right? Water column. Okay, I think I'm on the right track, Andrew.
Okay, on the right track, yeah.
So we do have the biogeochemical Argo floats. And with those complementing the satellite data, we have the potential to improve how we specify water column properties. Then there are LiDAR missions on track. They will also help improve the characterization of vertical structure. So there are potentials for improving those as well.
Okay. Yes. So I think we have covered all the questions. And I will thank again, Jeremy. Thank you for accepting the invitation or for giving this exciting and opening field of information about the ocean. And
Thank you for
I
the
will
invite.
thank, please. And also thank all the Trevor Platt Science Foundation members and students and the general audience that were here today. And especially also to Katarina from AIR for hosting this,
Yes, thank you.
webinar. And before saying goodbye, I would like to remind you all that the annual meeting of the Trevor Platt Foundation is scheduled to be on the 13th of August, so it's coming soon. And the agenda and the meeting link will be distributed soon. So please, all the members, make your best to attend. So with that, thank you very much and see you on our next webinar.
Thank you.
Thank you all.
Bye,
Thank you all.
everybody.
Thank
Bye.
you.
Bye.
Thank you all. Bye-bye.
Bye. Thank you.